Hi, in this video I show you how to calculate coefficients of Fourier series of a function in Matlab using Matlab FFT and also comparison of FFT results with analytical calculation. So let's say we have a function fx. We can write its Fourier series as follow. We have a constant a0, we have cosine terms, and we have sine terms. So the task for us is to calculate a0, an, and bn. N is from 1 to infinity. Analytically, we can calculate the coefficients using these integrals. For example, a0 is the average of the signal, an can be calculated by this, and so the bn. It's also very simple to show why an can be calculated by this formula. You just need to replace fx with this equivalent, and when you multiply it to this term and do the integration, everything simplifies, becomes 0, and only an will be left. So that's why this integral is equal to an. Same for bn. Now let us assume that we have a function. This is a sine wave, but the negative part is 0. So we want to calculate Fourier series coefficients with FFT and compare it with analytical calculation. Let us first do the analytical calculation. As I said, this waveform is a sine wave. So instead of fx, I put sine omega 0t. But this is only sine for the half of period. So we do the integration from 0 to half of the period. After integration and simplification, you get to conclusion that a0 is 1 over pi. We continue our calculation to find an. We need to calculate this integral. Again, fx is sine omega 0t. We do the integration from 0 to t over 2. We have multiplication of sine to cosine. We can convert it into summation. And then some basic high school mathematics. You can do the integration and simplification. Eventually, you come to conclusion that an is 0 when n is odd, and is this one when n is even. You can pause on any of these slides and follow the derivation if you want. Then we continue for bn. We need to calculate this integral. Fx is sine omega 0t. We do the integration from 0 to t over 2. Basic calculation, we get to here. It turns out that these two terms cancel each other, so bn is 0. But this is only true when n is not 1, because if n is 1, here we have 1 minus 1 in the denominator, which is not possible. So for case n equal to 1, we have to go back to here, and we calculate b1 by putting n equal to 1. So for b1, we have this one, omega 0t minus omega 0t is 0, cosine 0 is 1, and this term becomes cosine 2 omega 0t. Even though we are integrating over half period because we have a factor 2, this one becomes 0, and integration of 1 over this period is t over 2. T over 2 multiplied 1 over t gives us 1 over 2. So constant b1 is 1 over 2. So the Fourier series of this waveform is actually this one, constant a0, 1 over pi. We have the cosine terms. When n is odd, the coefficients are 0. When n is even, we have this one. And for bn, we only have b1, which is 1 over 2. And for all the other n's, bn is 0. Okay, so first let us construct this series and see how this waveform come into existence when we add more and more terms of this Fourier series. Okay, so I've written this code that adds different terms of this series together so we can see how the waveform is gradually constructed. I'm going to add maximum 50 terms of this series together. So the code is very simple. I'm not going to explain it. If you want to have the code, you just pause on this frame and copy the code. Here is the top part, and here's the tail of the code. Okay, let's run it. N equal to 0, we have the DC part, 1 over pi. N equal to 1, we only have a sine term. The cosine term is 0. So sine term plus that DC part gives us this one. N equal to 2, we have the cosine terms, which adds to the previous summation. N equal 3, we don't have any coefficients. N equal 4, we have another cosine terms, which adds to the summation. And basically for higher n, whenever n is even, we have a cosine terms, which adds to the previous summation and gradually shape the waveform. It's very amazing that using some simple cosine, sine, and DC, combining them, we can get such type of waveform. It's a much more complex waveform. So whenever I calculate Fourier series, really I get excited that these things can happen. And actually, it has a life lesson for my case, and that is um, even if we combine simple stuff at the right time with the right amount, we can achieve maybe something big or have a big impact. All right, so let us stop this excitement and we continue with our tutorial, and that is calculating these coefficients now with FFT of Matlab. Okay, so in order to calculate FFT, first I'm going to create a signal. I select the sampling frequency of 5000. This is the time vector from 0 to 0.8 seconds, and the steps is 1 over fs. Then we calculate the number of intervals, is basically the size of t minus 1. And then we create the waveform, is sine omega t, omega is 2 pi f. Frequency I selected 50 hertz here. And whenever the values are below 0, I set it to 0 so that we can create our waveform. If I plot it, you can see that the waveform is like this. Of course, here I selected 0.08, which means 80 milliseconds, so it's 4 cycles. So that's why we have 4 cycles. Okay, so we have created our data points, x. In some cases, obviously, you don't have a function for your signal. You have the values. For example, you measured it from oscilloscope. So in that case, you have already x. If you want to calculate L, what you have to do is just take the size of x minus 1. That gives you L, the number of intervals. And if you want to calculate Fs, basically, you have your signal, so you have the timestamps. So you can basically calculate the time steps between two consecutive data points, and Fs is 1 over that time step. So if you already have the waveform, you can calculate L and Fs very simply. All right, so we created the waveform X, and we also plotted it. Now we want to calculate its FFT. So Y is equal FFT of X. Now Y is a vector which consists of complex numbers. The length of Y is the same as X. We can use the elements of Y to calculate the Fourier series coefficients of X. How? As follow. So A0 is Y1 divided by L. AN is 2 times real part of yn plus 1 divided by L. And Bn is minus 2 times imaginary part of yn plus 1 divided by L. And obviously, we can also calculate the magnitudes of the harmonics. For the DC part, is the ABS of y1 divided by L. And for the harmonic, is square root of an power 2 plus bn power 2, which is equal to 2 times absolute value of yn plus 1 divided by L. However, there is a little bit of catch here. When I calculated the Fourier series analytically, I used this waveform. So the time period is 20 milliseconds, which is equivalent to 50 hertz. I did the integration and we found the coefficients of Fourier series for this one. The base frequency in that case was 50 hertz. When I wanted to take the FFT, I introduced this waveform. This is exactly like that, but it repeated 4 times. Now from MATLAB point of view, this whole is one waveform. So what is the base frequency of this waveform? So totally we have 80 milliseconds, and 1 over 80 milliseconds gives us 12.5 hertz. By the way, we can calculate this 12.5 hertz also by dividing Fs by L. Fs is 5000, the length of the signal is 400, that gives you 12.5. The equations that I mentioned, these terms, if we take FFT of this one, these A0, AN, and BN that we find by these equations, these are coefficients of Fourier series of this waveform, which has a base frequency of 12.5 hertz. Now the question is, how can I extract the coefficients of Fourier series of this one from the FFT of this one? Because they are almost the same, so we must be able to extract that. Okay, so let us look at this. Here if you put n equal to 1, so A1 is related to Y2. So A1 of the Fourier series of this is related to Y2, the FFT of this. Okay, so Y2 is related to the base frequency, 12.5. Y3 is related to 25 hertz. Y4 is related to 37.5, and Y5 is related to 50 hertz. So actually Y5 of FFT of this waveform, this one is corresponded to A1 and B1 of Fourier series of this waveform. So if you calculate FFT of this and you want to get coefficients of Fourier series of this original one, we have to actually use this formula. A0 is the same, is Y1 divided by L. However, AN is 2 times real part. Here we take the base frequency of these, in this case 50 Hertz. Base frequency of this is 12.5, so we divide them. 50 divided by 12.5, this gives us 4. So it's yn multiply 4, or n multiply that division, plus 1. So for example, A1 for this is related to y4 plus 1, so y5 of the Fourier series of this one. So B1 again is corresponded to y5 divided by L, and so on. Now there is another question, and the question is, why do we divide it by L? Okay, so let us look how MATLAB calculates Fourier series of a waveform. Basically, we say the Fourier series is this is the main waveform multiplied to Wn power this. Wn is nth root of 1. So if you replace this one here, you get to this one. Now let us look at first term of this FFT. y1. What happens to y1? Because we put k1, this one becomes 0 and e power 0 is 1. So it's summation of xj. So y1, this term, is summation of xj. Let's go back here. We said that a0 is 1 over the period multiply integration of the function. Here we have the summation in the discrete form. In the continuous form, this is integration. Okay, so we have the integration of the signal. So if we want to relate it to a0, we have to divide it by the period. Or in the discrete case, we have to divide it by the number of intervals. So that's why a0, or in this case actually should be a0. That's why a0 is related to y1 divided by L. And if we look at here, we see that for an and bn, we have a division by t and also a multiplication by 2. So that's why here we divide by L and also multiply by 2. Okay, so let us implement what we have learned so far. We say y is equal FFT of x. In this case, I'm going to plot the magnitude of harmonics. So we say P2 is ABS y over L. First element of P2, we keep it. But from the second element onward, I multiply it by 2. This is actually to replicate this situation. So first element is this. From the second element, we have to multiply by 2. So this is the magnitude of harmonics, the vertical axis. For the horizontal axis, we have the frequency. The base frequency in this case is Fs divided by L. And this is the vector. Now the vector is from 0 to L. The size of L is 1 unit less than x and y. But here, because we start from 0, the size of this vector is exactly the same as size of y. Okay, if I plot this, this is the magnitude of harmonics. But is this really the magnitude of harmonics? Let us have some observation. If we exclude the first one, from the second one onward, actually we can see that everything is exactly mirrored around this center frequency. Okay, but is it that, for example, at 5000 Hertz, really we have this magnitude of Fourier series? The answer is no. Let us look at the sampling frequency. Sampling frequency in this case is 5000. According to Nyquist's theorem, the sampling frequency should be at least 2 times than the highest frequency. So with 5000, the maximum frequency that we can get theoretically is 2500 Hertz. Actually, in this case, we cannot even get 2500 Hertz because the signal length was limited. So we observe that the signal is mirrored against this center frequency, and also from this center frequency onward, this information is not useful. We have to discard them. Okay, so that's why usually we plot single-sided amplitude spectrum. So I uncomment this. Here we define P1 is equal P2 from first element till half, and frequency is the same but until half, so until this frequency. I'm going to disable this. Okay, so if I plot it now, we have to plot P1. Okay, so these are basically the magnitude of harmonics of our waveform. Because previously we calculated the harmonics analytically, so I can also calculate the magnitude of them. And here you can see that they match with what we calculated from FFT. Now let me zoom in on this. Okay, so they match. You notice that as we move toward the higher frequency, toward this 2500 Hertz, the value that we calculated analytically is a little bit different than what FFT gives us. This is because, as I said, the sampling frequency is 5000. So, for example, at 2500 Hertz, we cannot capture the frequencies very accurately. However, if we increase the sampling frequency, let us make it 50,000. We plot the waveform, and now we calculate this again. Okay, again single-sided. Sampling frequency was 50,000, but we plotted the frequency up to 25,000 Hertz. And now I put the analytical calculation. Let us zoom in on this. So you can see that in this case, the magnitude that we obtain analytically and the values that we get from FFT MATLAB, they are much closer because the sampling rate is much higher. So at this lower frequency, we have better accuracy. Okay, so now I will show you why the FFT produced mirror results. Okay, so this is FFT. We calculate it like this. Here we can use Euler formula and replace this e power something with cosine and sine. Basically then the calculation yk becomes this one. You can pause on any of these slides and think about them. All right, so now I have yk is here. I'm going to compare yk with another element. So for example, y2, I want to compare it with yn. y3, I want to compare it with yn minus 1 and so on. So I'm going to change the variable. Instead of k, I put n minus k plus 2. So n minus k plus 2 goes there, n minus k plus 2 goes here. This n divided by n becomes 1, so this term will stay. This is the rest of it. Same way here. N divided by n is 1, so this coefficient stays here, and this is the rest of it. This is an integer multiply a full period, so the cosine can be simplified. Only this term will remain, and the same way for the sine. Only this term will remain. Okay, so we said that yk is here, and yn minus k plus 2 is equal to this one. But if you notice is that we know that cosine phi is equal to cosine minus phi. So actually, instead of 1 minus k here, I can write k minus 1. Nothing will change. And instead of 1 minus k here, I can write k minus 1, but put a minus here. Now, if you compare, this one is exactly the same as this one. Almost exactly the same. There is a minus here. So we say that yk is equal to conjugate of yn minus k plus 2. And actually, therefore, the magnitude of yk is equal to magnitude of yn minus k plus 2. So therefore, as you observe that around the mid-frequency, we have a complete mirror behavior when we plot the magnitude of the FFT. All right, so far we have calculated the magnitude of harmonics, and now we are going to finalize everything by calculation of coefficients of an and bn and comparison between analytical 1 and FFT. So everything is similar. So y is FFT of x. P2, in this case, we don't take absolute value. We just say y divided by L. So first element, we do nothing. Second element onward, we multiply it by 2. And then we take only half of this signal. Same way we construct the frequency vector. Fs divided by L multiplied to that vector. Okay, so this is for the analytical plot. This one is for the FFT plot. So we plot f versus the real part of P1. Okay, in this case, I am only plotting it for the first 65 harmonics. And the same way, we can plot the B ends, basically f versus minus image of P1. And again, I plotted only for the first 65 harmonics so that it shows more clearly. Okay, so we can see that these are Bn coefficients. We know that we only had one coefficient analytically. The bar is the one that we calculated analytically, and the dots are from FFT. And we can see we can exactly calculate that, and all the other one, they are 0. And here are an, this is a0, these are a1, a2, and so on. And because here we have now sampling frequency of 50,000, so you can see everything is very accurate. If I maybe decrease this, so this is the original waveform, and this is the comparison. You can notice that there are some little bit of error that appear here. For example, this one, the magnitude of these frequencies is now 0.01 and so on, but they actually do not exist in this waveform ideally. So now if I increase the sampling frequency again, you notice that so those values, they actually decrease. So now it's much smaller. Of course, still they are there. This is, but it's one order of magnitude less. All right, so this is all for this video. I hope that you learned a little bit about how to calculate FFT with Matlab and compare it with analytical calculation. Bye.